Hello, this is Jeff Hamrick at the University of San Francisco's Financial Analysis Program, and I'm going to talk for a few minutes about using the Skewness-Kurtosis test to check whether or not the residuals from a linear regression model are plausibly normally distributed. So I've got here the body fat percentage data set that we've used quite a few times in class, and I'm just going to create a regression model from this data set quickly. Let me regress body fat percentage against, let's say, age, height, abdominal circumference, ankle circumference, and bicep circumference. Okay, so here's our model, and we can use the predict function to extract the residuals from the model. So I create a set of residuals, predict my residuals, and then the option R or the option comma residuals. This will generate a new variable for us that is the residuals from this multiple linear regression model. So there are a number of statistical tests supported by Stata, and in fact Stata only supports a small subset of all of the statistical tests for normality. One of them is the Skewness-Kurtosis test, which is a variation upon the Jarque-Bera test. What it does is it looks at properties of the skewness and kurtosis of the raw data. In this case, we'll be using the residuals in place of actual raw data. And it takes a function of the sample skewness and the sample kurtosis that is approximately chi-squared with 2 degrees of freedom. And now it turns out that it's not really all that close to being chi-squared with 2 degrees of freedom. So rather than run the proper Jarque-Bera test using a chi-squared test statistic, the Skewness-Kurtosis test in Stata uses a bootstrapping procedure to make an adjustment for the fact that the Jarque-Bera test really is only an appropriate test when you have a large number of data, hundreds and hundreds and hundreds of data, 600, 700, 800, or thousands of data, a large number of data. The Skewness and Kurtosis test has also basically been fairly well criticized by people who work with data on a day-to-day basis. It tends to not give you good information about how your data are violating normality, and it tends to reject the null hypothesis of normality very easily, okay? And what's worse is sometimes when you deviate from normality, the deviation from normality is in fact not all that important. It's not something that somebody with experience in data analysis would worry all that much about. So I would urge you to use the Skewness-Kurtosis test in Stata with some level of caution, okay? So you run it with the command skTest, and then you simply use the variable that you'd like to test. Let me make one more quick caveat here. The Skewness-Kurtosis test is really intended to be designed to be used on data that's raw data that we think might come from a normal distribution, like perhaps height data of males. Residual data is not raw data. It's derived from a regression model, and parameters are estimated in order to generate the residuals. So it's a bit of a hand wave, and purists would object to this. But we're probably safe to treat the residuals as themselves being a raw data set that we'd like to test for normality. Okay? So I just do skTest on my residuals, and I get this output. There's a couple of things that you can think about doing here. So this gives you a p-value connected to just the skewness, the sample skewness of the of these residuals, of the fitted residuals from this regression model. Under certain conditions, the sample skewness, if you normalize it in a particular way, will be asymptotically approximately normally distributed. So this is a p-value based on that particular statistic, sample skewness. Similarly, after a certain normalization, the sample kurtosis is also asymptotically approximately normally distributed, and then you can get a p-value if that kurtosis is far out of whack from what you might expect under the assumption of normality. And here is the p-value associated with just looking at the sample kurtosis. Okay, so what the Jarque-Bera style test does is it uses both of these quantities together in a kind of test that we call a portmanteau test. And we've got two quantities then right here. A chi-squared test statistic that has been adjusted for the fact that the Jarque-Bera test takes a very long time to converge to a chi-squared distribution with 2 degrees of freedom, and then the p-value associated with this adjusted chi-squared test statistic. So I recommend that you focus most of your attention on this quantity right here. That quantity takes into account both skewness and kurtosis, and it has been adjusted for the fact that we have a small sample size here, 252, not the thousands of data points that we might hope to have for the Jarque-Bera test. So because this p-value right here is not very small, it's not under the standard significance threshold of 0.05, I would not reject the null hypothesis of normality. And I would conclude that at this time we don't have enough evidence to view these residuals from this regression model as being something other than normally distributed. Okay? So this is only one lens onto the normality of the residuals. You have to use other devices like histograms, density plots. You have to use QQ plots and PP plots, and maybe other statistical tests like the Shapiro-Wilk test or the Kolmogorov-Smirnov test. But nonetheless, the Skewness-Kurtosis test should be one tool in your toolbox when you're assessing the fitted residuals for conformity to standard regression assumptions. Let me know if you have any questions.